Hello, everyone. In this section, we will look at how the simulation engine processes thermal loads to size your equipment, and why importing the correct design day files is the mandatory first step for any successful error-free HVAC simulation. Let's dive in. Compared to zone HVAC equipment, air loop and plant loop systems can be significantly more complicated to build from the ground up. Creating them manually requires assembling many components and carefully defining how they connect. In upcoming lessons, we'll look at how to construct these loop-based systems step by step. For now, however, it's helpful to start with a faster approach: HVAC system templates provided in OpenStudio. These templates allow you to quickly generate common HVAC system configurations. Many of them are loosely based on system types described in ASHRAE 90.1, Appendix G, which is widely used for energy modeling and performance comparisons. A template can be used exactly as provided, or it can serve as a starting point that you later modify to match the details of your project. As an example, consider ASHRAE 90.1, Appendix G, System Type 7. This system represents a multi-zone variable air volume, served by a central air handling unit. The air handler supplies conditioned air to multiple thermal zones, and adjusts the airflow to each zone according to its load. Inside the air handler, there are typically both cooling and heating coils. The cooling coil receives chilled water from a chilled water plant, while the heating coil receives hot water from a hot water plant. The chilled water plant itself is served by a water-cooled chiller. When the chiller removes heat from the chilled water, that heat must be rejected somewhere else. This is handled through a condenser water loop, which carries the heat to a cooling tower where it is released to the outdoor environment. When this entire configuration is modeled in OpenStudio, it typically involves 3 plant loops and 1 air loop: a chilled water loop supplying the cooling coil, a hot water loop supplying the heating coil, a condenser water loop connected to the cooling tower, a central air loop serving the building's thermal zones. While it is technically possible to construct all of these loops and components manually, doing so can be time-consuming. In practice, it is usually much easier to begin with an OpenStudio HVAC template, which automatically assembles the basic system structure. From there, you can adjust components, controls, and parameters to better match the system you want to model. Let's look at how we can quickly add a template HVAC system in OpenStudio. Inside the application, go to the HVAC System tab. In the upper left corner of the interface, you'll see a plus button. This is where you can select and add HVAC templates. When you click this button, an Add HVAC System dialog opens. In this dialog, you can scroll through a list of common system configurations. Each option represents a different typical HVAC setup. For example, if you're trying to model something similar to ASHRAE 90.1 Appendix G, System Type 7, the closest match in OpenStudio is the template called Packaged Rooftop VAV with Reheat. Once you select this template and click Add to Model, OpenStudio automatically creates all of the required air loops and plant loops, along with their main subcomponents. You don't have to build everything from scratch. For this particular template, OpenStudio adds 4 separate loops to your model: 1 air loop that represents the central air handling unit, a hot water plant loop, a chilled water plant loop, and a condenser plant loop. These loops are already pre-connected with the appropriate components, so the chilled water, hot water, and condenser systems are all tied into the air handler in a realistic way. After the template has been added, look near the top of the HVAC tab. The System Selector field, which previously showed something like Service Hot Water, will now switch to VAV with Reheat. This indicates that you are currently viewing the air loop that represents the central air handler. You can use this same System Selector field to navigate between different loops and systems in your model, switching from the air handler to the hot water loop, the chilled water loop, the condenser loop, or other systems you may have added. In this way, HVAC templates give you a fast, structured way to build complex systems, and then you can refine or customize them as needed. Next, let's talk about auto-sizing HVAC systems in OpenStudio. By default, most HVAC systems and components in OpenStudio are auto-sized. This means that key parameters, such as airflow rates, heating capacity, cooling capacity, and other performance limits, are not manually defined by the user. Instead, they are automatically calculated by the Energy Plus simulation engine. Energy Plus determines these values using built-in sizing algorithms that respond to the thermal loads coming from the building's thermal zones. The sizing process happens in several steps and follows a top-down cascading approach. First, Energy Plus performs a load calculation for each thermal zone. This calculation is based on extreme design weather conditions, representing the hottest and coldest scenarios the building might experience. The idea is to determine how much heating or cooling is required to keep each zone at its thermostat setpoint during peak conditions. If this sounds familiar, it's because the concept is very similar to the ideal air loads approach we discussed earlier, where the simulation determines the amount of energy needed to maintain indoor comfort. Once the heating and cooling loads are calculated for every thermal zone, those loads are combined to determine the total load that the HVAC system must handle. From there, the model begins sizing the individual system components. For forced air systems, the process usually starts by estimating the required supply airflow rate. This airflow is calculated using the zone load and an assumed supply air temperature. In systems that serve multiple zones, the airflow requirements for each zone are added together. This gives the total system airflow rate, which is then used to determine the capacity of the supply fan. After the airflow rates are established, the simulation uses those airflow values, along with design heating and cooling temperatures, to size the heating and cooling coils within the system. Now, this explanation is intentionally simplified. In reality, Energy Plus uses very detailed and sophisticated sizing routines that can handle many different HVAC configurations and system types. Still, the key concept to remember is this: even though you may not manually assign capacities to your HVAC equipment, every component in the simulation ultimately receives a specific size. Those sizes are calculated automatically by Energy Plus based on zone loads, internal gains, and extreme weather conditions. However, there is one important caveat. The capacities generated by auto-sizing don't always match equipment that exists in the real world. Sometimes the simulation produces components that are smaller or larger than typical commercially available systems. This can happen for several reasons, but a common cause is simplifications in the model, especially assumptions related to thermal zoning. For that reason, OpenStudio also allows users to override auto-sizing. If needed, you can explicitly define equipment capacities using hard-sized values, which fix the component size instead of letting the simulation calculate it automatically. Now let's talk about design day files, which play a critical role in the auto-sizing process. As we discussed earlier, OpenStudio relies on DDY weather files to represent the extreme outdoor conditions used for sizing HVAC equipment. If your model includes any auto-sized HVAC components, you must have at least one design day defined, otherwise the simulation will fail to run. In practice, almost every OpenStudio model that includes HVAC ends up with at least one auto-sized parameter. So, including design day data is essentially required for accurate and error-free simulation. You may remember from previous lessons that DDY files are imported through the Site tab. When you load one of these files, OpenStudio brings in a set of predefined design day conditions. A typical DDY file includes several different design scenarios, representing a range of heating and cooling extremes. However, OpenStudio imports only two of these by default: the 0.4% summer design day and the 99.6% winter design day. These numbers describe the probability of temperature exceedance. For summer, a 0.4% design day means the outdoor temperature will exceed this value for only 0.4% of the year. For winter, a 99.6% design temperature means the outdoor temperature stays above that value for 99.6% of the hours in the year. These rare extremes help Energy Plus determine how large the HVAC equipment must be to maintain comfort under peak loads. Once the DDY file is imported, the Site tab automatically updates to show the loaded design days. If needed, you can also add or remove design days manually using the buttons provided in the interface. In short, design day files are essential inputs that guide Energy Plus in correctly sizing your HVAC systems under extreme but realistic conditions.